Okay, so welcome back. We're going to finish up this week's session by starting a discussion of goodness of fit. And first, I want to ask the question of what does it mean to say that a model fits? And so let's denote the observed outcomes as y1, y2, up to y sub n. And remember that the y's are either zeros or ones in the context of logistic regression. So we have a bunch of ones and zeros, and then we denote the predicted values of the model as the probability that y is equal to 1. So what you hope is that when the person actually has y equal 1, say when the person dies, that they had a high probability of dying. And you hope that when the person lived, they had a low probability of dying. In the example I gave about the woman who had open heart surgery, is a very sad story. And she was a case where she had the outcome y equal 1, but a very low probability that y is equal to 1. However, the probability was not 0. So although the probability didn't even come close, if everybody who had a probability of only 3%, if everybody lived, that would not be a good estimate of the probability. Okay, nobody said your probability of dying is 0. They said, so again, thinking about what probability means, to say a probability of 3% means that 3 out of 100 will experience a bad outcome. And it's rarely given to patients in that kind of, in that kind of detail. I mean, they think, oh, 97%, I'm going to do great. And fortunately, most of the time they do, if it's a good model. If it's a good model. So we'll denote the values of the predicted values as the probabilities, and we're going to conclude that the model fits if the summary measures of the distance between the observed responses and the predictions of those responses is small. So if, in fact, most of the time when people get y equal 1, they have a high probability, and most of the time when y equals 0, they have a low probability, then, in fact, the distance between y and y hat will be small, and you'll have good fit. And not only that, if the contribution of each pair, that is each pair y and y hat, over all people, to these summary measures is unsystematic and small relative to the error structure of the model. So what I mean by that is that if you have good fit most of the time, but it turns out that for one particular racial group, it's always bad fit, and race is not in the model, then it may mean that you can improve your fit a lot just by including a variable about race. So, and there you see there's a systematic error, and the systematic error may be caused by the fact that you don't have enough variables in your model. So we're going to concentrate on the first point. The second point, the contribution of each pair, that's something we call logistic regression diagnostics. And it's out of the range of this course. I would suggest that if it's something you're interested in, you can find a lot of information on it in our book. But for now, we're going to concentrate on the first point, and that is the computation and evaluation of the overall measures of fit. Okay, so what I want to do now is I want to talk with you a little bit about the goodness of fit tests and concepts that we need. And the first concept that I need to talk to you about is I need to talk about a covariate pattern. And what is a covariate pattern? Now, covariate pattern, as the name suggests, is a particular configuration of the covariates. So, for example, if I had a model and the model had sex and smoking, and so I have two sex groups, and I have, say, smoking was smoke or don't smoke, how many covariate patterns are there? Well, you can have women smokers and women non-smokers. And you can have men smokers and men non-smokers. So the total number of covariate patterns is 4 covariate patterns. So let's suppose that I was going to do this study, and as people entered the study, we grouped them into covariate patterns. So for example, the study is going to go on, and I know that those are the only 2 variables in my model. So the first person who comes into the room is a male smoker. And so we say to them, okay, as a male smoker, you're the first person in the study, you're the first male smoker, why don't you get into this bin? And the bin happens to be this big cylindrical tube, but inside it's nice, there's a couch and there's a TV and there's a, there's a refrigerator and there's beer in the refrigerator. So, so he climbs into the tube and he sits on the couch, kicks his shoes off, grabs a beer, watches some sporting events, happy. Okay? The next person's a woman non-smoker. So she comes in, she's the first woman non-smoker. So she gets to start her own tube. So she jumps into her bin, sits on the couch, does whatever she wants, doesn't matter. She's happy. And finally, enough people come in, and now there's at least one person in each of the 4 bins. Each bin is a covariate pattern, right? And now, as the study's getting bigger and bigger, and we start to have hundreds and thousands of people in the study, what's happening in the bins? Well, the bins are becoming crowded. It's unpleasant. People are arguing about what show they're going to watch, or they're arguing about why you drink my beer, or there's some problem, and so it becomes a problem. People are basically climbing over the walls because it's too crowded inside. So by having few covariate patterns and lots of people, you have a lot of people in each covariate pattern. But then you enlarge your model and say, instead of having just smoking and sex, we'll put in a new variable like age, or like blood pressure, or like cholesterol level. And now, as soon as you start putting in these continuous covariates, now all of a sudden you're breaking out way, 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 way more bins. And so now everybody goes to their respective covariate pattern, and they may be unique. There may not be 2 people in the same covariate pattern. And once again, you're back in this very pleasant situation of everybody's by themselves, and they can do whatever they want, and they don't have to worry about their neighbors who have the same covariate patterns. You have to remember that any time 2 people share a covariate pattern, they have exactly the same probability of the outcome, because the covariates determine the probability. Okay? And again, the more continuous variables in the model, the more potential covariate patterns there are. Okay? The next thing I want to talk about is I want to talk about this idea about the probabilities reflecting the true outcome experience of the data. So let's say that we did our low birth weight study, and after the study was over, we invited all of the women to come back to our study site, and we said we just want to have a follow-up. But when they came back and they signed in at the registration desk, they were not given a name tag to wear, but they were given a probability tag to wear. And the probability tag was when they were in the study, what their probability of having a low birth weight baby was based on her covariates, right? So based on whatever covariate she had, we know her probability of having a low birth weight baby. She's wearing that on a tag, on a string around her neck. We've got her probability. And so all of the 189 women come back, and they all have now a probability tag. And then, there's hors d'oeuvres and there's drinks, and it's very pleasant. And then somebody gets on the microphone and says, "Okay, I'd like to welcome you all here, and we're glad you're here. We'd like to ask you if you would mind to get into a line and arrange yourself in order with the woman who had the lowest value for the probability of a low birth weight baby." Or we didn't even tell them what the probability is. We say, the woman who has the lowest number, go here on the left, and the woman who has the highest number, go to the right. So you have a big long line now of 189 women long, and they're arranged in order on the basis of their probabilities. The lowest probabilities on this side of the room, and the largest probabilities are on that side of the room. Right? Get the picture? Big long lineup. And now, what we're going to do is we're going to start on the left side of the room, and we're going to march off the lowest 10% of the probabilities. Okay? That is, the 10% of women who have the lowest probabilities of having a low birth weight baby. Okay? We call that group the lowest decile of risk. Okay? And then we have the next lowest decile of risk. And then finally, at the right side of the room, we have the 10% who have the highest probabilities. That's the 10th decile of risk. All right? Now let's say I said to you that the average probability of having a low birth weight baby among the women in the first decile of risk was 5%. The average was 5%. How many low birth weight babies do you expect to see in the first decile of risk? To make this simpler, instead of 189 women, let's assume there are 200 women. So let's assume that the first decile of risk has 20 women. Okay? And I'm telling you that the average probability is 0.05 among those 20 women. How many expected low birth weight babies would you have? And if you think about it, you realize that 0.05 is the average, which means that the sum of the probabilities was 0.05 times 20, which means that the sum is 1. And the sum of the probabilities is the sum of the y's, if you remember from an early slide. So that means that you expect to have one low birth weight baby among the 20 women who are in the first decile, right? The average probability is 0.05. You have 20 women, so you expect one low birth weight baby. So you expect one low birth weight baby in the first decile. Suppose I told you there were two in reality. What would you think about the model? Probably not too bad, right? What if I told you there were three? Again, probably not too bad. But if you get to 4, 5, suppose I told you there were 8 low birth weight babies and you expected one. At what point would you begin to say, this model's not really telling me what it should be telling me? And by the same token, at the upper end of the room, there's 20 women up there, and supposing I told you that the average probability of having a low birth weight baby among the 20 women in the highest decile of risk was 0.6. Average, 0.6. How many low birth weight babies do you expect in the top decile of risk? Well, 0.6 times 20, you expect 12. You expect 12 low birth weight babies in the top decile of risk. Suppose I told you there were 11. No problem, right? 10, no problem, right? 13, no problem. What if I told you there were 3? So at some point, your comfort level with whether the probabilities being produced by the model are matching up with what was actually observed in the data is beginning to deteriorate. Okay? So this idea about the correspondence of the observed number and the expected number is really important. And it tells us something about whether or not the model is producing probabilities that reflect the true outcome experience in the data. Okay? So having said that, we now have the background that we need to do a formal discussion of goodness of fit testing in the 7th week of the course, which we will do next time. So have a good time with the homework. And again, remember to look at the homework solutions, and as you do that, I think you'll be able to work your way through the material very well. Okay, so have a good time, and we'll see you next week.